Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutewa Sos Ukobela Wemets. And without any further ado, let's look at these questions that we have here. Okay, so we have question 6 still on chemical equilibrium. It says initially 60.8 gram pure carbon dioxide, CO2 is reacted with carbon in solid state in a cell container of volume 3 dm cube. The reaction reaches equilibrium at temperature T according to the following balanced equation. Then, as you can see there, 6.1 is saying define the term chemical equilibrium. So we know how do we define chemical equilibrium. We say chemical equilibrium is a dynamic equilibrium. A dynamic equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. Right. And then that's our definition like that. So a dynamic equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction is called chemical equilibrium. Right. Then here we are told at equilibrium, it is found that the concentration of the carbon dioxide is 0.054 mole per dm cube. Then 6.2.1, it's saying calculate the equilibrium constant Kc for this reaction at temperature T. Right. So in order to calculate this is what we need. So we have our chemical equation there. And then to drop down the coefficient as our ratios, we have 1, 1, and then 2 here. But then we are told that initially the concentration of carbon monoxide at equilibrium is 0.054. So if we take this one here as the carbon dioxide block, and this one is the carbon, and then this one is carbon monoxide, that means the 0.054 needs to be here, right? And then remember that initially they only sealed that reactant into the reaction vessel. So that means the concentration of your carbon monoxide at the beginning of the reaction is 0 because that is the product. So the products are not formed yet. Okay, but then when we read further, we can see that here we can actually find the number of moles initially of the carbon dioxide, because we are told initially 60.8 gram pure carbon dioxide is reacted, right, with carbon. So to calculate the number of moles of carbon dioxide initially, we'll have to say mass over the molar mass, right? And then the mass we are given is 60.8. Then the molar mass for carbon dioxide, that will have to be 44. Now the number of moles of carbon dioxide initially, when we punch that into our calculator, that's 1.382. So I'm rounding off to 3 decimal places because even our concentration here is rounded to 3 decimal places, right? So I'm going to have here 1.382, right? And then now, in order to calculate the number of moles at equilibrium, remember I already have the volume. The volume we are given that it is what? 3 dm cube. Now I can do a reverse calculation here and calculate the number of moles. So to calculate the number of moles, I only need to take the concentration, then multiply it by the volume. So if I take the 0.054 and then multiply it by the volume of 3, then I get 0.162, right, for the equilibrium number of moles of the carbon dioxide. Now, in order to get the change in the number of moles, now I do understand that it's just a matter of taking this, subtract that so that I can find the change in the number of moles. So 1.382 minus 0.162, that will give me 1.22. Now to find the the change in the number of moles of the carbon monoxide, I obviously have to use ratios. So remember, when we get to the change block, that's where we now apply our ratios. The change block always relates to the ratio block. Then now, a ratio of 1:2 tells you that at this point here, I must have twice the number of moles, because what am I going to say? It's 1.22 multiplied by 2, then divided by 1, right? So that will give me 2.44, right? So that means I can find the equilibrium number of moles here, because this is a product. I know if the forward reaction is favored, then for the product, I need to say that's initial plus the change is equals to the equilibrium. So 0 plus 2.44, that will give me 2.44. And then now I can even use that to find my concentration here. So have the number of moles at equilibrium. To calculate the concentration, it's simply number of moles divided by the volume. So the volume, remember, it's 3 dm cube. So 2.44 divided by 3, I'm going to get 0.813. That is rounded off to 3 decimal places. Now, why am I not concerned about filling this block here? So I deliberately made this block here, and then I did not fill it so that I can kind of make you understand that every time you have a substance that is in solid, we do not need its concentration. So it doesn't matter having to fill this block here. Right. So because this is a solid, we don't mind if we don't actually fill in that block, because remember, we are not concerned about the concentration of solids. The concentration of solids is always the same throughout, right? It's constant throughout. So it never makes it to the Kc expression. For the Kc expression, we only put substances that are in gaseous state or aqueous state. So that's why we do not fill in the table in here or the values in here, right? So, okay, now to calculate the Kc, we are already through now. So it's just a matter of taking our concentrations and then simply substituting them into our Kc expression. So to do that, we're going to say Kc. So allow me to just write over here. So I'm going to say Kc is equals to the concentration of the carbon monoxide, which is the product, and then square, because it has a ratio of 2, over the concentration of a carbon dioxide, which is a reactant, and then it has a ratio of 1, so we're just going to leave it like that. Now I'm not going to include carbon because it's a solid. So we have 0.813, and then that will be squared over 0.054. Now, having to punch that into your calculator, what do you get? You get 12.24, and that becomes your Kc value, right? So note how we did that. Okay, so now let's proceed. Okay, then 6.2.2 says the minimum mass of carbon that must be present in the container to obtain this equilibrium. So if we are to go back here, you will find that the change in the number of moles of the carbon dioxide here is 1.22, right? So if we were to come here and fill in this part here that we did not fill in order to find the minimum number of moles that will react of the carbon, obviously we have to check the ratios here. Now the ratio is 1:1. That means the number of moles of carbon that need to react in order that this reaction reaches equilibrium is only a minimum of 1.22. Only what is enough for it to react with the carbon dioxide. So this is the number of moles that we are going to use. So the assumption here is that we want our carbon to be the limiting reagent. So that means it will be completely used up in that chemical reaction, meaning the initial number of moles would have to be 1.22, and also the number of moles that will be used up would have to be 1.22, meaning at equilibrium, if it is a limiting reagent, it reaches equilibrium at with the number of moles of 0. which you do understand that it won't have concentration at that point, right? So that's the assumption with that question, that we need to find our carbon here as a limiting reagent. So that means we must have enough to just react all of it. So now to calculate that, we will use the number of moles, 1.22, and then find the mass that needs to react there. So how do we do that? We know our stoichiometry, that's N is equals to M over big M. So the number of moles that we got there, it's 1.22. Then we are looking for the mass over the molar mass. What is the molar mass of carbon? Molar mass of carbon has to be 12. When we cross multiply here, we have mass is equals to 14.64 gram, right? And then we have it like that. So awesome. Now 6.3 is saying, how will each of the following changes affect the amount of carbon monoxide at equilibrium? Choose from increases, decreases, or remains the same. They say more carbon is added to the container. Now, if more carbon is added to the container, you do not say this will. We know that increasing. So number one, let me clear this up. We know that increasing the concentration or the amount of a reactant will obviously favor the forward reaction, and then will lead to more products being formed. But then here, the case is you have increased the amount of a solid. So when you increase the amount of a solid, nothing really happens, because remember, concentration is only focused on substances that are either in aqueous state or in gaseous state. So if it's a liquid, if it's a solid, then there is no effect on the concentration. So that means even if you add more carbon atoms there, or you add more carbon particles, nothing will really happen to the reaction vessel, and then that will not change our values at the equilibrium, or shift the equilibrium, right? So here we are supposed to say remains the same. Remains the same, because we have increased the concentration of a solid. And then 6.3.2, the pressure is increased by reducing the volume of the container at constant temperature. Note that what are they doing? They are increasing the pressure. Now, why are they saying by reducing the volume? Because pressure and volume are inversely proportional. So note always how they ask that question. So sometimes they might say the volume is increased. You need to note how to relate that to the pressure, right? So explaining this, we know that number one, so you know the method that I use. Number one, I come with the observations. Then that's when I will answer the question that says increase, decrease, or remain the same. So number one, we know for sure that an increase in pressure favors the reaction with less number of gas moles. With less number of gas moles. Now, if we go back here and then try to find our sum of coefficients for the gas molecules, we're not going to take the coefficient for this one because it's a solid. So we only have one, the coefficient of carbon dioxide. And then on the right-hand side or product side, we have two. So based on this, we can see that the reaction that will have to be favored is the reverse reaction, because less number of gas moles is produced on the reactant side. So we then say the reverse reaction is favored. The reverse reaction is favored. And then if the reverse reaction is favored, what will happen to the amount of the carbon monoxide? Obviously, what is a reverse reaction? It is a reaction that promotes the using up of product to form back the reactants. So that means the amount of carbon monoxide gas decreases, right? So the amount of carbon monoxide gas decreases as a result of the reverse reaction being favored. So our answer now has to say decreases. And then there you go, 3 marks. Okay, now let's proceed. We have 6.4. It says the table below shows the percentages of carbon dioxide and carbon monoxide in the container at different temperatures. Now 6.4.1 is saying, is the reaction exothermic or endothermic? Refer to the data in the table and explain the answer. Let's give them the observation. The yield, so I want you to fixate your eyes here and note what is happening. The carbon monoxide, remember, this is our product, right? And then we can comment on whether the reaction is exothermic or endothermic based on what is happening to the product. If the products are increasing, that would mean the forward reaction is favored, right? And then if we look at our temperature is increasing. Now, if our temperature is increasing and also the amount of the product is increasing, that tells you that this reaction that was favored favors an increase in the temperature, right? Or is being favored by an increase in the temperature. So that means we say the yield of carbon monoxide gas increases with an increase in temperature. So that's an observation. As the temperature increases down the table, also the percentage yield of carbon monoxide increases. And then I'll say an increase in temperature, but an increase in temperature favors the endothermic reaction, according to our Le-Chatelier's principle, favors the endothermic reaction. Therefore, the forward reaction is endothermic. So as simple as that. So the forward reaction is endothermic. Okay, then 6.4.2 says, use the information in the table to determine temperature T. Show clearly how you arrived at the answer. Right. So in order to tackle this, we need to go back to our results for the KC, but then I will only be taking you to this final part here, where we had C is equals to N over V, the concentration. So concentration at equilibrium. Now, the concentration at equilibrium for carbon dioxide, we were given here 0.054. And then the one for carbon monoxide is the one that we did calculate, and then we found 0.813. Right. So if you can just run it back, you will see those values. Then 0.054 and then 0.813. Now, I like to base everything on my product here. So in order to calculate the percentage the percentage yield, meant to say, this is what we would do. We'd say, let's find our concentration total. That means the total concentration for both these substances, 0.054 plus 0.813. And then we find that it is 0.867 mole per dm cube. Now, if I want the percentage yield for the carbon monoxide, we'll say, okay, percentage yield of carbon monoxide, that's the concentration of the carbon monoxide, 0.813, over the total concentration of both the substances. So we want to find that of what is produced from carbon monoxide, what percentage is it of the total concentration, then multiplied by 100. And then when we punch that into our calculator, we find 93.77 degrees. But I only calculated the percentage yield. Why am I calculating the percentage yield while they ask me to find the temperature? It's because the temperature yield that I get has to correspond to a certain temperature. And then if I find a percentage yield that corresponds to that certain temperature there, then we need to then say the temperature T is that. Now, when we check here, 93.77 corresponds to the temperature 827. So therefore, temperature T is equals to 827 degrees Celsius. And that's how you were supposed to tackle that question there, for a total of 22 marks all in all. So it was a very interesting question. Make sure that you play this video as many times as possible and just try to understand the approach that I took into solving all this. But with all that being said, please press the thumbs up button if you've enjoyed the lesson and then you have found it helpful. And if you've been watching the videos and haven't subscribed yet, please hit that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.